So today we're speaking about reinforcement learning, and this is really one of the most successful areas in which psychology, neuroscience and artificial intelligence have interacted in many interesting and exciting ways. This work started in psychology towards the end of the 19th century, the late 1800s, and was inspiration for artificial intelligence, reinforcement learning, that then went on to help us understand various aspects of how this type of learning works in the brain in neuroscience. And in turn, those neuroscience findings have continued to inspire new reinforcement learning algorithms. Reinforcement learning is also one of the most exciting areas of artificial intelligence today, and it continues to push the boundaries of what's possible for neural network models to achieve. So some of you have asked for a bit more reinforcement learning in the course, so we're going to try go quite quickly through from the basics to some of the more exciting recent developments in the field.
The greatest teacher failure is.
So despite Luke Skywalker's shocked face, reinforcement learning really is fundamentally about learning from your failures and your successes. So by the end of this video, you will understand the goal of reinforcement learning, as well as some fundamental elements of any reinforcement learning algorithm and setting. We will learn about some algorithms for learning the values of states and actions. We will learn the basics of reinforcement learning in the brain, as well as some brain-inspired advances that have helped the emerging field of deep reinforcement learning. We will learn how the brain builds cognitive maps and how this is connected to the idea of model-based reinforcement learning. And we'll also learn how reinforcement learning is starting to tackle some advanced aspects of cognition, including metacognition, or learning to learn, as well as things like curiosity, which might seem like very human aspects of cognition. And throughout this lecture, I may use the abbreviation RL to mean reinforcement learning from time to time. So previously, we focused on supervised learning, where a network takes in some input and it creates some output, and a teacher tells it how far away from some target output its response was. And based on the error, the difference between its own output and the target, the neural network will update its weight. And in this scenario, this correct output, the target, is given by some sort of a teacher who is in some way all-knowing. However, in reinforcement learning, we have an agent. It could be a neural network, it could be a robot, it could be something else. This takes an input and it generates an action. And this action acts on the environment. It may lead to the environment changing from the current state to a new state, and it will generate some sort of reward. So in the English language, we normally think about rewards as being positive, but in the framework of reinforcement learning, rewards can either be positive or negative if they have a value below zero, or they can be neutral if their value is exactly zero. And we also get information about the current state from the environment. And the goal of reinforcement learning is to maximize the total amount of reward in the future. So imagine we're at a state at time point t, we move on to the next state and we receive a reward, and then we move on to the next state after that, we receive some other reward, again it could be positive, negative or zero, and so on. And we want to maximize these total amounts of rewards as much as possible. Usually, however, we discount future rewards to reflect the fact that we would prefer a situation in which we receive our rewards as soon as possible. So we can think about this total amount of discounted rewards as follows, where the reward, total reward in the future, is equal to the reward at each time point summed up, with each future time point discounted by a factor gamma according to how far in the future it is. And this gamma will usually be between 0 and 1 to appropriately reflect the idea that future rewards are a little bit less valuable than current rewards. And in practice, a gamma of around 0.9, for example, is often used to reflect this preference. Now, you don't need to know this information for this course, but if you're reading the literature, this total amount of discounted future reward is often called the return, and that might be given some other symbol, such as G here. So each reinforcement learning system has a few elements in common. It always has an agent, which is the thing that performs the task, the robot, the neural network, etc. It also requires an environment, so the external system that the agent interacts with. And this encompasses everything that is outside of the agent's control. So it's everything that the agent observes and also responds to. And a reinforcement learning system also needs a reward signal, which is usually just a single number, which can be positive, negative, or 0. And this is sent from the environment to the agent at every time step. And the agent's only goal is to maximize the total reward it receives over the long run. And as we mentioned earlier, this can be appropriately discounted for future rewards. So reinforcement learning is very related to some classical ideas in psychology, including Pavlovian conditioning. And this is a type of learning where you learn to predict which stimuli are associated with rewards. Here, in psychology, the word conditioning is normally used, and in this context, conditioning essentially means learning. So in Pavlov's classic experiment, before any learning, he presented a dog with food, and he observed that the dog started to salivate, indicating that it liked the look of the food, it was hungry, etc. So this food is called an unconditional stimulus because it doesn't require any learning in order to generate this response, this salivation. And the salivation is called the unconditional response, again, because it doesn't require any learning. And again, before learning, he presented a different stimulus, ringing a bell. And this was thought to be a neutral stimulus because it was neither particularly positive or negative for the dog at this stage. And this bell ringing, as you might expect, it didn't produce any kind of noticeable response in the dog, and the dog did not salivate when it heard the bell. Then Pavlov presented on many different trials a bell ringing followed by the food. In the beginning, the dog would start to salivate in response to the food, but after learning, Pavlov could present only the bell alone without any of the food, and the dog would indeed salivate in response only to the bell. So the dog here had learned some sort of an association between this neutral stimulus, this bell, and the reward, the dog food. So this bell initially didn't have any particular value for the dog, but after repeated associations with the food, the bell itself appears to have acquired some sort of a value for the dog that leads it to expect food and therefore salivate. This bell is called the conditional stimulus. So this is one of the most famous experiments in all of psychology. And are we able to explain this result from a reinforcement learning point of view? So in order to move towards that, let's learn about the fourth element of a reinforcement learning system, and that is a value function. And a value function is what specifies what is good for the agent in the long run. So imagine if we start in a state at time point t, and then we transition to the next state at time point t.1, and as we move from one state to the other, we receive some sort of a reward. So imagine our state at time point st is little s, then the value of that state is equal to the total amount of discounted future reward that we can expect to accumulate over the future starting from this particular state. So have a little think, and you can pause the video if you want, but what's the relationship here between the value of this state at time t and the value of the following state. If you like, you can pause the video here and have a little think about that. Turns out that the estimated value of the current state, shown here as big V of st, is just the estimate of the value at the next state, discounted because it's one step in the future, plus the expected reward received during the transition to the next state. So here the value of the state at time t plus 1 would be this part of the equation starting from s of t plus 1. Okay? So there are several reinforcement learning algorithms that try to take advantage of this recursive relationship. And one of the most important algorithms is the temporal difference learning algorithm. And this TD learning, or temporal difference learning, can actually explain quite a lot of what happens in classical Pavlovian conditioning. So imagine here again, we're at this state at time t, s of t, we transition to the following state and we receive some reward. So now that we've transitioned to the following state and we've seen the reward that's taken place, we have a little bit more information about what the value should have been for the previous state. In particular, we've seen the reward during the transition and we've seen the following state. Okay, so probably our value estimate of the previous state should be a bit closer to the discounted value of the following state, plus the reward we've seen during the transition. And in particular, this difference between this updated information, the reward and the discounted value of the next state, the difference between that and the previous estimate of the value of the previous state, this is known as the temporal difference error. And in neuroscience, this is often called the reward prediction error. Although there are actually some different formulations of the reward prediction error. So the difference between these two terms on the left and the term on the right can occur if either the reward was higher or lower than expected, or the value of the successor state was higher or lower than expected. And the TD learning model updates the estimated value of the previous state based on these surprising rewards and surprising values of the following states. So if we want to update this value of the previous state, we start with the estimated value of the previous state and we move it in the direction of this new estimate using the reward prediction error. And this size of this update towards this new information is determined by a learning rate alpha. An example simulation of the temporal difference learning algorithm, and here we see several trials from trial 0 up to about trial 200, and in each trial there are about 40 different states. So in this context we can consider each time point within the trial as being a state of this reinforcement learning problem. We have a reward time over here, and we have the time of the conditional stimulus here. So in the case of Pavlovian conditioning and Pavlov's original stimulus, this would be the time of the dog food, and this would be the time of the bell. On the first trial, we're not expecting the reward, so we see this reward prediction error at the time that the food is given, which is in this context exactly the same as the temporal difference error. However, on the following trial, then we update our values of our states, and in particular the value of the state just before the reward is increased a little bit because it's followed by the reward. And on following trials, the states just before that are then followed by a state with unexpectedly high value. So what we see is this propagation backwards in time of this value signal from the time of the original reward to eventually going back to the time of the conditional stimulus, which in Pavlov's case was the bell. And noticeably this reward prediction error actually essentially goes away at the time of the reward. So this was a real simulation, and here we see the main idea translated to the case of Pavlov's experiment. We have food at time t. On trial number 1 we get this reward prediction error when we see the food that we weren't expecting. But after a couple of hundred trials of learning, we see that this reward prediction error has travelled back in time from the time of the food to the time of the bell ringing. So this is all about studying behavior and learning, which is essentially psychology. But how does this relate to what's going on in the brain, in neuroscience? So it turns out that this reward prediction error is extremely similar to signals that we see in particular neurons in the brain. Those are the dopamine neurons that we've mentioned before. So Wolfram Schultz and colleagues did many experiments recording from the dopamine neurons in the brains of monkeys while they performed a range of tasks that involved reward. Here we can see a task similar to that in Pavlov's dog, where a monkey is given an unexpected reward, juice in this case, and we see that these dopamine neurons fire consistently in response to the reward. Here again, each line here is a neuron on a particular trial, and each dot is a spike, an action potential from the neuron, and we can see that this neuron consistently fires in response to the reward shown here at time r with this line here, and above is a histogram showing the sum of all of these spikes across trials. However, after learning there's a particular stimulus that predicts this reward, similar to the bell in Pavlov's experiments, we see that this dopamine neuron firing has moved back from the timing of the reward, shown here in R, to the timing of the conditioned stimulus, CS here. And now we see a lot of dopamine firing in response to the conditioned stimulus just after it, and we see actually no real difference in dopamine firing in response to the reward. So I think a lot of people who aren't neuroscientists have the idea that dopamine is related to reward, but these days most neuroscientists think that dopamine is actually much more closely related to the reward prediction error. It was in fact Reid Montague and Peter Dayan, two computational neuroscientists, who recognized this pattern in Wolfram Schultz data and saw that it was extremely similar to this temporal difference learning error from reinforcement learning. And this reinforcement learning approach to understanding dopamine neurons' activity has really been one of the major successes of computational neuroscience over the last few decades. More recent experiments in mice have enabled the quantification of the actual dopamine released from the dopamine neurons to their targets, and they've seen very similar patterns. In particular, here we have a similar experiment where a mouse is given a water or juice reward at a certain time, and there's a particular odor that predicts this reward. And what we see is that on the first day we see this big dopamine release in response to the reward, but we can actually see the timing of this dopamine signal move backwards in time with learning over days, and the size of the dopamine response at the time of reward gets smaller and smaller. So this dopamine signal seems to strongly resemble the reward prediction error in the brain. And in particular, this temporal difference learning has been one of the most successful algorithms at relating RL to the brain. So now we're going to talk a little bit about the anatomy of the dopamine system. So dopamine primarily comes from a relatively small number of neurons in the midbrain, two little areas that you don't necessarily need to know, called the substantia nigra, which just means the black substance because it's a little bit darker than neighboring areas, and the ventral tegmental area. Here we can see that these neurons originate here in the midbrain. They go up and they target structures in the center of the brain, particularly the striatum, as well as different parts of the cortex. And here we can see the dopamine receptor density, which is the receptors on the neurons that receive the dopamine. They're extremely high in this structure. This is the same structure that's drawn here, called the striatum. They're extremely strong here, so there's a lot of dopamine going on in this structure called the striatum. But there's also quite a lot of dopamine in particular parts of the cortex, such as the orbital frontal cortex, which is thought to be very important for kind of value-based learning, reinforcement learning in the brain, but also generally parts of the cortex near the top of the cortical hierarchy, prefrontal cortex, parts of the parietal cortex, etc. We know that apart from being important for reward prediction error, reinforcement learning, dopamine is also essential for working memory. And John O'Doherty and colleagues found, using fMRI scanning of human subjects, that the brain activity in these regions that receive a lot of dopamine on these reinforcement learning type tasks, the activity in those regions actually also resembles the reward prediction error. Please go to Blackboard now and try to solve this problem using the TD learning algorithm shown a few slides back. So until now, Pavlov's experiment and the TD learning algorithm that we saw is all about passively learning if particular situations or states, as they're known in reinforcement learning, are associated with future rewards. However, reinforcement learning starts to become really interesting when the agent can learn actions to perform that will change the environment. In psychology, this learning of which actions to take is known as instrumental conditioning. And some of the principles of this are summarized in Thorndike's law of effect. And Thorndike came upon these ideas by studying the behavior of cats in boxes like this. These experiments, which perhaps would find it difficult to get approval from a modern ethics committee, nonetheless were very instructive to Thorndike's thinking at the time about how we learn to take actions, and some actions and not others. So here we can see an image of a cat in a box, in Thorndike's box, and Thorndike would put certain types of levers or hooks on a certain part of the box, and the cat would have to learn to open the door by pulling on the correct hook or lever. Here is an example of one cat and the amount of time it took to escape the box across about 70 different trials being put in the box over and over again. And what we can see is that at the beginning it tended to randomly move around the box, perhaps swipe at different things, and it would take quite a long time, about 3 minutes on average, to escape the box. What we see is that over many different trials, the average time to escape goes down from about 3 minutes to some much shorter time, less than a minute. And Thorndike's quite wordy explanation of this was as follows. So, of several responses made to the same situation, those which are accompanied or closely followed by satisfaction to the animal will, all other things being equal, be more firmly connected to the situation so that when it recurs, they will be more likely to recur. So that means that if the animal makes an action in a particular situation and it leads to a reward or something positive, it's more likely to do that action again. He goes on. Those which are accompanied or closely followed by discomfort to the animal will, all other things being equal, have their connections with that situation weakened so that when it recurs, they will be less likely to occur. So this means that if the animal makes an action and something negative happens, for example, it gets shocked, it's less likely to repeat that action. And it says, he goes on to finish the quote by saying, the greater the satisfaction or discomfort, the greater the strengthening or weakening of the bond, which means that the amount of learning of how much you should repeat this action is in proportion to how positive or negative the reward or punishment is. Essentially, this is the basis of learning from trial and error. So in order to build a reinforcement learning system that is actually able to act and learn from trial and error, we need to implement the fifth part of the system, which is a policy. And a policy is the mapping from each particular state to the probabilities of selecting each possible action. So here we see that the policy, often represented as pi, of a particular, so the policy often represented as pi gives the probability of taking any particular action in any particular state. Now that we have a reinforcement learning system with policies and actions, we need to update our definition of the value function. So in any system in which an agent takes actions, the value functions, which we saw before, are defined with respect to a particular policy that is being followed. And this is because the value of any particular state is going to depend on the policy that you're taking to select your actions. So we learn the value of particular actions with these action value functions. So imagine that we're in this state at time t, And now, instead of passively transitioning to the next state, we take an action, and that brings us to some following state, and we receive a reward. So the value of taking an action A in a state S under our policy pi is the total amount of discounted future reward that an agent can expect to accumulate over the future, starting by taking action A in our current state S and following the policy pi afterwards. How do we actually select these actions? Well, there are a few different possibilities, but one of the most common action selection mechanisms is known as epsilon greedy. It's as follows. At each state, with a probability 1 minus epsilon, we select the action with the highest value, and then with a probability epsilon, we select randomly among all of the possible actions. Learning agents usually have to try to balance exploitation and exploration. Exploitation is where you take the actions that you think are best at that particular time in order to maximize your estimated reward. Whereas exploration allows you to see, for example, if there's some actions that you have neglected in the past that may actually lead to better and more rewards. And there are several different possibilities of trying to balance this exploitation and exploration, and that may depend on the particular problem at hand. One example is starting with a relatively large value of epsilon, so you do a lot of exploration early in learning, and then as you learn the problem, you reduce the value of epsilon and you start to exploit more and take the highest value action almost all of the time towards the end of learning. So it's this epsilon greedy action selection mechanism combined with an estimate of the action value function Q, that combination of an action selection mechanism and an action value function defines a policy. So now we're ready to move on to our first action performing reinforcement learning algorithm, and this is the famous Q-learning algorithm. So in Q-learning, the estimated value of an action taken in the previous state is updated using the reward prediction error, and the size of the update is determined by the learning rate again. And to calculate the reward prediction error, we need the old estimate of the value, our estimate before seeing the reward that was given on the transition to the following state. We subtract this old estimate from the reward received plus the value of the following state action pair. So we see it's very similar to TD learning, but instead of state values, we use action values, and that's the values of actions in particular states. When we're updating the value of the previous state action pair, which following action should we use to update these values? Should we use the value of the next action that we really chose, or should we use the value of the best possible available action? So imagine that we chose the highest value action in the first step, and in the following step we chose a random action by following the epsilon greedy policy, but this random action might have been quite bad. It might have randomly moved in an undesirable direction. So should we reduce the value of our previous state action pair due to this random action? Or should we say, well, we know there was a better available action there, so that shouldn't affect this Q value of our previous action? These two methods are actually both used in reinforcement learning. On-policy methods are those where you learn according to the actions that you really took. An example of this is the algorithm called SARSA, where you update based on the first state and action, and then based on the reward and the state and the following action, giving us the letters SARSA. And the alternative is off-policy methods, where we update our Q values based on the best possible available following action. And Q-learning is a classic example of off-policy reinforcement learning. Here we can finally finish our update equation for the Q values, for the action values. And we update using the discounted value of the best possible following action according to our current beliefs. And in practice, in all of these methods, the values of particular actions in particular states are stored in a kind of lookup table, which is updated as we learn. So here we can see in state 1 we might have 4 possible actions, and we learn a positive value for actions 1 and 2 and a negative value for action 3, etc. So please turn to the blackboard and answer the following question. So we saw how the temporal difference error was strongly related to the activity of dopamine neurons in the brain. But what about these action values or cue values? So in a recent paper, Shin and colleagues studied the behavior and neural activity of rats exploring and performing a task in this environment here, where they had to go over this central plank and turn to the left or to the right. And a reward was given on the left or to the right with some changing probabilities. At the beginning, it was 63% probability of reward on the left and 21% on the right. After a certain number of trials, the probability switched. Then it switched back to more probable rewards on the left, and then it switched again. And we can see here that the rat's choice, the probability of choosing left, matches very closely the prediction from the cue learning algorithm. They then went and recorded neural activity from different parts of the brain. Here we can see an example of a neuron in the striatum whose firing seems to represent something similar to the action value, the cue value. In fact, here it's actually an inverse of the cue value. And they went on and found that these action value type signals were in neurons in different parts of the brain, including the striatum and the orbital frontal cortex, which we saw have a lot of dopamine receptors, as well as in the hippocampus. So we saw that in cue learning, the action values are stored in a kind of lookup table. But what if there are many, many different possible states, so that the state space is so large that you can't possibly explore it all? Well, this is a problem that deep cue learning was built to solve. So, for example, in real life, our sensory input differs from moment to moment. And so it's very hard to say that you're in exactly the same state as the one that you were at any moment before. So how do we get over this? Is each moment its own state? In these kind of realistic environments, having a lookup table for each state and action seems to be infeasible. There just seems to be a huge amount of possible states and indeed a very large number of possible actions. So what's the solution? Well, the solution proposed by people at DeepMind was to use a deep neural network as an approximator of the cue value function, that is the action value function. And in a particularly famous example of their paper from 2015, they gave in to a deep feed-forward neural network a series of frames from video games, in particular 4 frames in a row of a video game, and they said that each state was a particular sequence of frames from a video game, and the output of this deep neural network was the estimated value of each possible action from that state. So essentially they're using this deep neural network to approximate the cue action value function over this huge state space. And their idea at the time was really inspired by the recent success of convolutional neural networks and other deep feed-forward networks in supervised learning. So they thought, can we make reinforcement learning a bit more like supervised learning? So their idea was to use something very similar to the reward prediction error from cue learning as the loss function for their deep neural network. And in particular, they use this term on the left, which is the new estimate of the action value after seeing the reward in the next state, as the target in order to update the parameters and to improve the estimates of the value of taking actions in particular states. So that the idea is that gradually, over time, this cue value function becomes more and more accurate and similar to the real cue value. And one of the effects of taking this approach, deep cue learning, is that similar states will acquire similar action values. And this, in many real-life situations, actually tends to be quite a helpful property, which allows us to generalize action values to new states that we've never actually experienced. So one of the problems with using these deep learning approaches to estimate the action value function was that these consecutive states in reinforcement learning tend to be highly correlated with each other. So that means that if you're updating parameters regularly, you may completely change your network based on some local properties of the environment, so that you might become very good at learning the action values in one particular part of the environment, but that might not generalize well to other parts of the environment. You may know that the founder of DeepMind, Demis Hassabis, was actually a neuroscientist. So the team from DeepMind was inspired from neuroscience to come up with a solution to this problem. And the solution that they came up with was to learn not online as you go, but to learn from replaying past experiences, which are states, actions, and the transitions from one state to another that action led to, as well as the reward obtained on that transition. So the agent stores these experiences in a kind of memory bank, and then it replays these experiences randomly and uses this for training. And this is one of the tricks that allowed the team at DeepMind to have incredible success with this algorithm. Please turn to Blackboard and answer this quiz question. So the team at DeepMind were inspired by the replay of memories, but how does that actually work in the brain? So memory replay in the brain was discovered by looking at the activity of a particular type of cell in the hippocampus. And these cells are known as place cells. They were discovered by John O'Keefe and colleagues in the early 1970s when they were studying the activity of cells in the hippocampus as rats ran around different environments. And they found that a particular cell would fire very strongly in a particular location and much less strongly elsewhere. So these cells responded to particular places, and they were known as place cells. So you can imagine that if a rat is running down a hallway, there might be one cell, this iron cell, that will fire for location A here, another cell that will fire for location B, etc. So Wilson and McNaughton in 1994 decided to study what happens in these place cells, not just during the behavior running around this hallway, but also during sleep. And what they found was that during sleep and also at rest while awake, the neurons that fired during that day's behavior reactivated in a similar sequence in the hippocampus. And more recently, something similar has been seen in some areas of the cortex. And it's thought that this reactivation or replay of the memories during sleep may drive memory consolidation or the strengthening and generalization of memories. These tricks that enabled DeepMind to combine deep learning with reinforcement learning enabled some exceptional performance on a whole range of video games. And in particular, we can see here a huge suite of Atari video games. All of these are different games, and here we see the performance of the deep Q-learning agent, and all of these games are at above human level performance. So this was really a remarkable step forward in the capability of neural networks. However, the network did still do very badly on some games, and in particular games like Montezuma's Revenge. It got 0% on, and this is a game that requires planning and has quite infrequent rewards. So how can we promote something like planning in a reinforcement learning agent? So now we need to start thinking about another element of a reinforcement learning system. So you can have reinforcement learning without this, so it's not really one of the essential elements. It's really important and opens up a lot of new capabilities. So I think it's worth considering as the sixth and most important optional element of a reinforcement learning system, and that is a model of the environment. A model of the environment is anything the agent can use to predict how that environment will respond to its actions. So a reinforcement learning system with a model, which is known as a model-based system, can simulate the next state. It can simulate an entire trial or perhaps all possible trials. And it can learn value functions from these simulated experiences and use these simulated experiences to improve its policy for when it really goes and interacts with that environment. And this entire process of simulating, learning value functions, and learning from that is known as planning. So to distinguish model-based reinforcement learning systems from the others, we call a reinforcement learning system without a model-free system. Let's turn to Blackboard and answer the following quiz. So now we're going to go into the distinction between model-free and model-based reinforcement learning a bit more deeply. And there are many different related distinctions in neuroscience and psychology. The distinction between model-free and model-based reinforcement learning closely parallels the ideas in psychology of habits and habit-driven behavior from a more cognitive, goal-directed behavior. It also distinguishes trial and error learning from learning through cognition and the development of cognitive maps. And also it's closely related to two often opposing approaches and theories in psychology, which is behaviorism and cognitive psychology. So we already learned about Thorndike and his development of these ideas of trial and error learning. And this is closely related to ideas from behaviorism. We try to think that all behavior, essentially even quite complex behaviors, are learned reactions to stimuli. And the approach that behaviorists encourage is to ignore completely unobservable mental processes, aspects of cognition and subjective experiences. And they think that these are, in a way, outside of the realm of science. There were, however, as early as the 1920s, results that put a doubt on this idea that everything was learning from trial and error. So Blodgett had rats navigate an environment like this freely without any rewards, which according to these earlier theories should not result in any learning. And he compared 3 groups of rats. So there was a start position here, and there was a goal position here, which on certain days would contain food. What he found when he compared 3 groups of rats, here we can see the days on the x-axis and the number of errors on the right axis. He compared rats that had reward food in the environment every day to rats where food was only introduced after 3 days and where food was only introduced after 7 days. For the rats that had food introduced only after 3 days and only after 7 days, that there was an immediate drop in the number of errors that these rats made, indicating that these rats had in fact learned a lot about how to navigate this maze towards this reward location, even though there was no food there yet. So this suggests that they'd built up some sort of an understanding of the environment without any rewards or without any kind of trial and error learning. So this suggests that the environment can be learned without explicit rewards or penalties. And this should not actually be possible with this trial and error or model-free reinforcement learning. So this is a kind of learning without reinforcement in a way, and suggests that animals can learn associations between different stimuli or different states by experiencing these sequences of states or sequences of stimuli as they explore an environment. So these results and others that followed it were a forerunner to cognitive psychology, which would eventually break off from this strict behaviorist view and approach to psychology. So what about people? Do people use model-free or model-based reinforcement learning? So this is commonly assessed with this 2-step task developed by Nathaniel Daw and colleagues. In this task, on each trial, participants have to choose between 2 spaceships. This is a first stage choice. Each spaceship will take the participant with a certain probability either to a red planet or to a purple planet. The participants then make a second choice, and these choices between 2 aliens, and they're rewarded with a space treasure or not. And the probability of receiving a reward from each particular alien changes over time. So the key analysis, in order to understand if somebody is using model-free or model-based reinforcement learning, is as follows. Imagine that you take a first-level choice. You choose the blue spaceship, and instead of the high probability transition to the red planet, the low probability transition occurs. The blue spaceship takes you to the purple planet. And then if you get a reward on this planet, on the next trial, should you be more likely to choose this blue spaceship, or should you be less likely to choose this blue spaceship? So the model-free reinforcement learning agent would be more likely to choose the blue spaceship again, because you want to reinforce the actions that you've taken that led to a reward, whereas the model-based reinforcement learning agent will realize that this transition between states was low probability, and that in fact if you want to reach the purple planet again, you should actually be more likely to choose the green spaceship and less likely to choose the blue spaceship. So here we can see the probability of repeating this first stage choice for a model-free learner, and it's exactly the same following a common transition and following a rare transition. However, for a model-based learner, for following a rewarded rare transition, you're much less likely to repeat the action. So this is how the behavior of these two reinforcement learning agents looks. What about humans? So it turns out that adult humans tend to use a mixture of model-based and model-free reinforcement learning. Their pattern of responses looks somewhere between the model-free and model-based learners. However, children use more of a model-free reinforcement learning approach. It looks actually very similar to the model-free reinforcement learning agent. And adolescents act somewhere in between, actually quite similar to the adult pattern of learning. Interestingly, adult patients who've had lesions to the hippocampus, for example due to a stroke or a brain injury, they tend to revert back to more of a model-free strategy on these types of tasks. So putting these together suggests that model-based reinforcement learning in the brain develops at some point over childhood and adolescence, and probably depends, at least in part, on the hippocampus. So how can we simulate model-based learning? So model-free reinforcement learning, you start with a value on a policy, you take an action, you have some experience, a reward, a punishment, you see the next state, and then you go and update your value and perhaps update your policy. However, with model-based reinforcement learning, there's also an outer loop that you also, based on the experience, you update your model of the environment, how likely particular states are to follow other states and actions, etc. And then you update your model, and then you can use that to plan, and you can use that plan also to update your value or also update your policy. So one model-based reinforcement learning is called DynAQ, and in DynAQ, learning and planning are accomplished by exactly the same algorithm, and this operates on real experience for learning and on simulated experience for planning. So the algorithm for DynAQ, shown here in pseudocode from Sutton and Bardo, starts out exactly with Q learning. So you start from the current state, you execute an action, for example using the epsilon greedy policy, you observe the reward and the next state, and then you update your Q values, your action values for taking that action in that particular state, based on the observed reward and next state. So this is exactly the same as model-free Q learning. However, in addition now, you also store the reward and the following state to update your model of the environment. Then DynAQ simulates or plans what would happen if it takes a particular action in a particular randomly selected state that it's already observed. So it starts from this randomly observed state that is stored in its memory. It simulates what would happen if it take an action. Based on this model, it simulates the reward and the following state, and this is then also used to update the action value function, and we can do this many more times for each actual step taken in the real environment. And here we can see performance on this task where you start from the state here and you have to find your way towards this goal state. So here we can see on the x-axis the number of episodes, which is the same as the number of trials, and we can see how many steps the algorithm takes per episode. We can see in regular Q learning, model-free Q learning, with 0 planning steps, it takes several hundred steps per episode, and gradually over dozens of episodes goes back down to quite good performance. However, the DynAQ algorithm with 5 planning steps does it a lot better, and with 50 planning steps, n equal 50 here, it has exceptionally good performance almost from the second trial. So it seems like planning can dramatically improve performance and learning on at least some tasks. This idea of learning the relationship between states and the environment is closely related to another idea called the cognitive map in psychology and neuroscience. A classic experiment demonstrating the idea of the cognitive map is by Tolman and colleagues. They placed a rat in an environment like this, where there was a little hallway out, and it had to navigate around these corners to eventually reach a goal state. And it learned this environment. It found its way to the goal, to the reward, on several days, and it got quite proficient at that. Then one day, this rewarded path was blocked, but a number of other paths were opened up. and these went off in different directions. Now, if it was purely using trial and error learning or model-free reinforcement learning, it would know that this particular direction is rewarded, but all of these other directions would have equal probability as they'd never been tried before. It turns out the rat was able to correctly select the shortcut to the reward, even though it had never taken this and never stepped down this path before in its life. So this suggests that the rats are likely learning a map of the environment in their mind, a kind of a cognitive map of the world. So in other words, the rats must have some sort of a mental model of the environment. So how is this cognitive map represented in the brain? So we've already learned about the famous place cells in the hippocampus that fire preferentially in particular locations. In the late 2000s, the Moser lab, which is now in Norway, recorded from the entorhinal cortex, which is the main input to the hippocampus. And they discovered cells that responded not at just one location in an environment, but they responded at evenly spaced locations in a kind of hexagonal grid all around the environment. And these cells were therefore called grid cells. And here we might be able to make the parallel between these navigation problems and reinforcement learning more obvious if we consider that each location in an environment could be considered a state in a reinforcement learning problem. And these discoveries, which together were called the brain's GPS, the place cell and the grid cell system, was awarded the Nobel Prize in Physiology or Medicine in 2014. That went to John O'Keefe and Edvar and May-Britt Moser. So far we've talked about cognitive map, so a map of a kind of physical space. But what about problems that don't involve navigating space? This question was asked by Constantinescu and colleagues in 2016, and they asked human participants to navigate around a very abstract type of space. In particular, human participants were given controls that allowed them to stretch out or shorten the neck length of particular birds and also the leg length. So in a way you can think about this as a kind of a two-dimensional space where the two dimensions are the neck length and the leg length of the bird. Whenever they reached particular locations in this space, they were shown a particular type of Christmas decoration, like a Santa Claus, a Christmas tree, etc. At some point they were given a particular bird to start with, and they were said, okay, you're starting at this point here, Santa Claus, please change the neck and leg lengths accordingly in order to navigate to the sleigh. And humans remarkably were able to learn this and learn to navigate this space. And they were able to do this in the fMRI scanner. And what Constantinescu and colleagues found was that certain regions of the brain, the orbital frontal cortex, the entorhinal cortex that are involved in spatial navigation and valuation, they encoded this abstract space using a kind of hexagonal grid. It seems to be essentially the same as the one used to navigate physical space. And indeed, the more they decoded this hexagonal coding pattern from the brains of individual participants, the better these people were able to perform at the task. So this suggests that the same grid systems that are used to navigate physical space may be used to plan and navigate abstract problems. So the cognitive map, although it was originally used to describe a map of physical space in the mind, you may actually have cognitive maps of all sorts of abstract problems that allow you to navigate and plan all sorts of difficult problems. So now for the final part of this video, we're going to relate some recent advances in reinforcement learning to some of the ideas we talked about way back in week 1. We learned in week 1 that metacognition, or strategies to improve metacognition or learning to learn, were some of the most effective techniques at improving learning in students. And recently researchers have been interested in whether reinforcement learning agents can learn to learn better. In particular, in this paper, again by the group at DeepMind, led by Jane X. Wang, they trained a recurrent neural network with LSTM units using model-free reinforcement learning. Here as inputs to the reinforcement learning agent, they had the state, the previous action, and the reward that was just received. And they were able to output the action and a value estimate. So they trained the weights on this network to approximate a value function from model-free reinforcement learning. And they got this network to try to perform the famous two-step task. Interestingly, when they were testing this network, they froze the weights so that there can be no more learning of synaptic weights, as this agent is meant to learn to perform this two-step task. Here's a reminder, is the pattern of responses you would expect from a model-free learner, and here is the pattern of responses you would expect from a model-based learner following a rewarded trial that occurred following a rare transition. And here's the results from the model behavior. And remarkably, this model behaved in a way that was much more consistent with a model-based reinforcement learning approach. So how is this possible? Well, they built this model knowing that deep and recurrent neural networks can approximate essentially any input-output function. And they reasoned that these models may be able to approximate even things like the model-based reinforcement learning algorithm. So essentially this model-free reinforcement learning algorithm that updated the weights of the network was able to induce learning of a model-based reinforcement learning algorithm in the dynamics and activity of the network. So in a way, this is learning to reinforcement learn. So I thought that this was quite a remarkable paper for the theory of learning in the brain, and it demonstrates that perhaps not all learning is occurring at the synapses, but some learning might be occurring on shorter timescales, perhaps just in the changes in activity in a neural network and perhaps in the brain. So the classic experiments demonstrating learning to learn in psychology were performed by Harlow, and they're described here in this paper in 1949. And Harlow trained monkeys on the following task. The monkeys were shown one of two stimuli, which were picture cards, and one of these stimuli was rewarded and the other was not. And that was the rule, and the monkey first learns by trial and error which stimulus is rewarded, and then the stimuli are changed. So these two cards are replaced with two other cards. Now, if the monkey has learned the rule, it should know, after selecting one of the cards, the very first trial, after seeing if that's rewarded or not, it should know what to do for all of the subsequent trials until the stimuli are changed. So these monkeys do actually eventually learn this rule. Here in a single episode represents multiple trials with the same stimuli, and here we can see the results, the performance for individual trials. It always starts at chance performance 50%, and in the early episodes for the first stimuli, performance gradually increases, but after quite a few episodes with many different stimuli, you can see that already on the second trial the monkeys perform at near 100% accuracy. That suggests that they've learned this abstract rule and they're learning to perform these tasks better. So for each set of stimuli, the monkeys still need to learn which of the stimuli is correct and not, but they're able to do this much more quickly after they figure out the rule. So in a sense, these monkeys are learning to learn. So in this same paper by Jane X. Wang and colleagues, they simulated this task that the monkeys performed. So in order to do this, they embedded the reinforcement learning agent in a kind of a virtual reality where it was looking at a screen. So for this task, they connected the RL agent to a deep convolutional neural network that allowed it to process images. And they showed two stimuli on the screen to the RL agent. The agent had to learn to shift its gaze to select the rewarded stimulus. So ConvNet is used to present the different stimuli, and the recurrent neural network is trained as before with model-free reinforcement learning. And so they found very similar behavior of this deep reinforcement learning agent to that which was seen in the monkeys. This network, in a sense, learns to learn, so that after seeing several different combinations of stimuli, it's able to perform extremely well already on the second trial. So this learning to learn implies perhaps some sort of learning of the rule, which is not possible under model-free reinforcement learning. So here we've seen that recent advances in reinforcement learning are starting to get at learning to learn, which is a key aspect of metacognition, which in turn is extremely important for advancing and accelerating human learning. In week 1, we also touched on the importance of curiosity as a key element in human learning. And we learned that curiosity occurs whenever we detect a gap between what we want to know and what we already know. So we've seen several remarkable successes of reinforcement learning algorithms. And these tend to work very well in environments when rewards are given very frequently. But what if you're in a game or in an environment that gives feedback only rarely? So one possible solution to this is to create intrinsic rewards. And that is essentially what curiosity is a kind of rewarding feeling that we get that does not come from the outside, but it's due to our own motivations and interests. So here we can see the design of a reinforcement learning agent that has something similar to curiosity. This has some extra pieces that we haven't seen before. It has a meta controller, and this meta controller chooses amongst multiple short-term intermediate goals. And what this tries to do is it tries to maximize the future extrinsic reward, like a regular reinforcement learning agent. However, the objective of this meta controller is not to choose actions, but to choose short-term goals. The controller then chooses amongst actions like a regular reinforcement learning agent, but it doesn't choose actions in order to maximize the overall long-term reward. It chooses actions according to the current goal set by the meta controller. And then this critic unit gives out an intrinsic reward to the controller if the current goal is complete. And these kind of curious agents learn better in environments in which rewards are uncommon. So a few slides ago, we saw that the remarkable DeepQ network from the team at DeepMind performed extremely well on many different arcade games, but it did really quite abysmally bad on Montezuma's Revenge, which is a game that requires some planning and has very infrequent rewards. So this curious reinforcement learning agent actually performs much, much better on this task that has infrequent feedback and rewards. So it suggests that this curiosity type setup may be really good for approaching these types of tasks that don't give you a lot of feedback. So please turn to Blackboard and answer this question. So now let's recap. You saw that the goal of reinforcement learning is to maximize the total amount of discounted reward in the future. We saw that the temporal difference learning model successfully explains many aspects of classical conditioning, and this is kind of a state value prediction model. We saw that the reward prediction error from the TD learning correlates strongly with what we see in dopamine neuron activity in the brain. We learned that Q-learning is a successful off-policy algorithm for learning action values. We learned that deep reinforcement learning approximates value functions, and this enables reinforcement learning in environments with a huge number of states, so more realistic environments. The replay of past experiences, similar to what's seen in the hippocampus, helps deep reinforcement learning to learn. We saw that a model of the environment is anything that an agent can use to predict how the environment will react to its actions. And cognitive maps, a particular type of model of the environment, are built in the hippocampus, orbitofrontal cortex, entorhinal cortex, and potentially other areas of the brain. And we saw how an intrinsic reward signal, something like curiosity, can help agents learn in environments that rarely give out a reward. So if you're still eager to learn more, I'll send you to these references. And if this isn't enough, you can please contact me. Thank you.